Hello students, in today's lecture we are going to learn about oscillations, NCERT section 13.5 to 13.6. We will also solve example from 13.5 to 13.6. This is our disclaimer. Learning objective. After this lecture you will be able to understand velocity, acceleration and equation of force in simple harmonic motion. This is our index according to NCERT. So in today's lecture we will cover first 13.5 velocity and acceleration in simple harmonic motion. After that we will solve an example 13.6 and then 13.6 force law for simple harmonic motion, and last example 13.6. Alright, 13.5 velocity and acceleration in simple harmonic motion. Let's start by looking at uniform circular motion. So in the figure 13.11 we see a particle moving in a circle at a constant speed. The velocity of particle shown as v of t is actually the projection of the velocity vector of a reference particle moving around the circle. So now let's consider what we mean by uniform circular motion. Alright, so this is when a particle moves around a circle at a constant speed. Even though the speed stays the same, the direction of motion is always changing as the particle goes around. The speed of particle v in uniform circular motion is its angular speed omega times the radius of the circle A. So mathematically v is equal to omega A. Here v is the measured in meters per second, omega is in radians per second and A is in meters. For example, if omega is 2 radians per second and A is 0.5 meters, then V equal to 2 times 0.5, which is 1 meter per second. If we increase the radius or the angular speed of the particle increases as well. Now let's focus on the direction of the velocity. At any moment the velocity vector points along the tangent to the circle at the particle's position. So suppose the particle's position is at point P. Alright, so to find out the direction, so draw a tangent. This means the direction is always changing even though the speed stays constant. Alright, because at every point on the circle the tangent is different. Alright, so understanding this changing direction is important because it leads to the concept of acceleration in circular motion. Now if we focus on x component of the velocity, if v is the total speed of the particle at point P, we can use the geometry of the circle to find out how much of the velocity points along the x-axis at any moment. So in circular motion the velocity vector is always changing direction. So its x component will vary as the particle moves around the circle. This x component is what we observe as the velocity in simple harmonic motion, like a mass on a spring moving back and forth. Alright. The formula for x component of velocity is v of t is equal to minus v sine omega t plus phi. Here v is the constant speed of the particle in the circle. Omega is the angular frequency in radians per second. T is the time in seconds, and phi is the phase constant, which tells us where the particle started. The important point here is negative sign. The negative sign shows the direction of the velocity at different points. For example, sine omega t plus phi is positive, the velocity is negative, and vice versa. Now let's recall that v, the speed in circular motion, is equal to omega times a. You know, capital A is the radius of the circle or the amplitude of the oscillation measured in meters. Omega again is the angular frequency in radians per second. This relationship helps us uh, rewrite our velocity formula in terms of amplitude and angular frequency. So substituting v is equal to omega a uh, into our formula, we get v of t is equal to minus omega a sine omega t plus phi. Alright. This equation tells us exactly how the velocity changes over time for a particle in simple harmonic motion. Velocity depends on both the amplitude and the angular frequency, and it varies sinusoidally as the particle oscillates. So the equation v of t is equal to minus omega a sine omega t plus phi gives the velocity of the particle at any time t, where the negative sign in the velocity equation tells us that the direction of velocity is opposite to the positive x-axis at certain points in the motion. This is important because velocity is a vector. It has both magnitude and direction. For example, when the particle moves to the left of the equilibrium position, its velocity points in the negative x direction. So from equation 13.4, that is x of t is equal to a cos omega t plus phi, equation 13.9 gives the instantaneous velocity of a particle executing SHM, where displacement is given by the equation 13.4. So here we have two equations. X of t is equal to a cos omega t plus phi gives the position of an object in simple harmonic motion. Second, v of t is equal to minus omega a sine omega t plus phi. Alright. So this is the velocity. The velocity equation is 13.9. Shows how fast and in what direction the object is moving at any time. Both equations depend on time and the phase angle phi. We can obtain equation 13.9 without using geometrical argument directly by differentiating equation 13.4 with respect to t. This approach uses calculus and gives us a more general method for finding velocity in oscillatory motion. V of t is equal to dx of t upon dt, which means the velocity at any time t is the derivative of the position with respect to time. This equation is the fundamental concept in physics. Velocity is always the rate of change of position. So by differentiating uh, x of t, uh, we will find the exact formula for velocity. You know, x of t is what? A cos omega t plus phi. Alright. So let's perform the differentiation. So we have v of t is equal to uh, differentiation of a cos omega t plus phi, where a is a is constant. So it stays out front. We are differentiating the cosine function with respect to time, where the inside of the cosine is omega t plus phi. So using the property differentiation, cos a t plus b with respect to time is equal to minus a sine a t plus b. This tells us that the derivative of a cosine function is negative sine function multiplied by the coefficient of t inside the argument. So applying the rule, we get v of t is equal to this one, minus omega a sine omega t plus phi. This matches the velocity equation we show at the start. Velocity depends on both the amplitude and angular frequency, and it reaches its maximum when the sine function equals 1 or minus 1. So we have shown that differentiating the position equation gives us the same velocity formula as the projection method. This confirms that both the calculus approach and the geometric approach lead to same result. It's a good example of how different methods in physics can reinforce each other. Alright. Acceleration in simple harmonic motion. Alright. So the figure 13.12 shows a particle moving in a circle, and we are interested in how its acceleration projects onto the x-axis. So using projection method, we can also find x component of the acceleration. Alright. So in SHM, the motion along x-axis is what we are really interested in. So but before we can find that x component, we need to know the net acceleration of the particle. The net acceleration is the total acceleration acting on the particle at any instant. Net acceleration determines how the particle's velocity changes as it moves. Since the particle is moving in a circle at a constant speed, it's undergoing uniform circular motion. Alright, that means the tangential acceleration, which is the rate of change of speed along the path, is 0. So in other words, at is equal to dB upon dt, rate of change of velocity, is equal to 0, because the speed is not changing, only the direction is. So to find the net acceleration, we only need to consider the centripetal acceleration. Centripetal acceleration always points toward the center of the circle and is responsible for changing the direction of velocity. Alright. Now let's focus on the centripetal acceleration of the particle moving in a circle. Centripetal acceleration is always directed towards the center of the circle, and its magnitude can be written as v square divided by a, or omega square a. Alright, here v is the speed of the particle, omega is the angular frequency in radians per second, and capital A is the radius of the circle. So the direction of this acceleration is always towards the center along the line from the particle to the center, which is labeled as PO. This one, PO in the figure 13.12. This is important because it shows that the acceleration is always trying to pull the particle back towards the equilibrium position, just like in SHM. Focus on both. Focus on that both the magnitude and the direction matter here. Acceleration is vector quantity. Means it has both magnitude and direction. Instantaneous acceleration of the projection along x-axis for particle P is then see figure 13.12. The instantaneous acceleration of the projection onto x-axis is what we are interested in. This is the acceleration that the particle would have if it were oscillating back and forth along a straight line. Alright. So the formula for acceleration in SHM is A of t is equal to minus omega square A into cos omega t plus phi. Alright. Here negative sign shows that the acceleration is always directed opposite to the displacement, pulling the particle back toward the center. For example, if omega is 2 radians per second, A is 0.5 meters and phi is 0, then at t equal to 0, the acceleration would be minus 2 square times 0.5 times cos 0, which is minus 2 meters per second square. Alright. So the formula A of t is equal to minus omega square A cos omega t plus phi. From equation 13.4, we have x of t is equal to minus A cos omega t plus phi. Therefore, A of t can be written as A of t is equal to minus omega square x of t. This is a key result for SHM. The acceleration is always directed towards the center opposite to displacement, and its size is proportional to how far the particle is from equilibrium. For example, if omega is 2 radians per second and x of t is 0.5 meters, then A of t is equal to minus 4 times 0.5, which is minus 2 meters per second square. Negative sign shows the restoring nature of the force in SHM. The acceleration A of t is always directed towards the center, and the value is given by A of t is equal to minus omega square x of t. So equation 13.11 gives the x component of acceleration of a particle in SHM. So here if we start with the velocity in SHM, which is v of t is equal to minus omega a sine omega t plus phi with respect to time. So we get the acceleration. Differentiating velocity gives us the acceleration formula. A of t is equal to derivative of v of t with respect to time. The main equation is A of t is equal to minus omega square x of t. For equation 13.11, acceleration of a particle in SHM is proportional to displacement. Alright, from the center, but in the opposite direction. That means the further you move from the center, the stronger the acceleration pulling you back. This is a defining feature of SHM, and it's why the motion repeats in a regular back and forth way. So for x of t is greater than 0, A of t less than 0, and for x of t is less than 0, A of t is greater than 0. The so the acceleration points to the right. This always pulls the particle back toward the center, no matter which sides it's on. Thus, whatever the value of x between minus a and a, the acceleration A of t always directed towards the center. This is what keeps the motion oscillating around the equilibrium position. Phase relationship in SHM. Phase relationships helps us understand how displacement, velocity and acceleration change over time for an oscillating object. So let's set the phase constant phi to 0. This means we are starting our measurement from the point where the object is at the maximum displacement. We will now write out the equation for displacement, velocity and acceleration as a function of time. So x of t is equal to a cos omega t. Uh, v of t is equal to minus omega a sin omega t, and a of t is equal to minus omega square a cos omega t. Alright, look at figure 13.13, which shows how displacement, velocity and acceleration all changes over time, even though they all repeat with the same period t. Their peaks and 0 points don't line up. This is what we mean by differ in phase. All three quantities follow a sinusoidal pattern, but they are shifted relative to each other. So look at here. A displacement versus time, B velocity versus time, and C acceleration versus time. So while all three quantities are sinusoidal, their maximum values occurs at different times. Alright, the phase difference is key to understanding how the motion evolves. For example, when displacement is at its maximum, velocity is 0 and acceleration is at its maximum in the opposite direction. So here in figure A, this is the maximum. Here in B, the maximum is this one, this point, again this one, and in C, this one. So displacement x varies from minus a to plus a, or uh, velocity v of t varies from minus omega a to plus omega a. So its maximum speed depends on both amplitude and angular frequency. For example, if a is 0.1 meters and omega is 2 radians per second, the maximum speed is 0.2 meters per second. Alright, and acceleration a of t varies from minus omega uh, square a to plus omega square a. This means the maximum acceleration depends on both the square of the angular frequency and the amplitude. For instance, if omega is 2 radians per second and a is 0.1 meters, the maximum acceleration is 0.4 meters per second squared. Alright, so plots of x of t, v of t and a of t in SHM. Let's look at how displacement, velocity and acceleration change over time for a particle in simple harmonic motion or SHM. The graph here shows all three quantities plotted along against time: displacement versus time, and velocity versus time, acceleration versus time. Alright, while they all repeat with the same period. Period is t in this, again period is t, both a and b, and period is here t. Their peaks and zero points don't line up. They are out of phase with each other. So x of t is equal to a cos omega t, v of t is equal to minus omega a sin omega t, a of t is equal to minus omega square a cos omega t. So let's use some trigonometric identities to rewrite these equations and see the phase differences more clearly. So cos pi by 2 plus theta is equal to minus sin theta, and cos theta plus pi is equal to minus cos theta. Above equations can be written as x of t is equal to a cos omega t, v of t is equal to omega a cos pi by 2 plus omega t, and a of t is equal to omega square a cos omega t plus pi. Alright, in other words, when displacement is at its maximum, acceleration is at its minimum, and vice versa. This phase relationship is fundamental to understanding how energy moves back and forth in a system. So here x of t is equal to a cos omega t, v of t is equal to omega a cos pi by 2 plus omega t, and a of t is equal to omega square a cos omega t plus pi. Phase differences with respect to displacement x of t plots. Phase difference means how much one curve is shifted left or right compared to another with respect to displacement x of t. We will see how the velocity and acceleration curves are offsets. This helps us understand the timing of motion in SHM, like when the object is moving fastest or when it's changing direction. So first look at the velocity plot. This one, velocity plot. It has a phase difference of pi over 2 or 90 degrees compared to the displacement. This means that when displacement is at its maximum, velocity is 0, and when displacement passes through 0, velocity at its maximum. For example, if a mass on a spring is at its furthest point, it's a momentarily stop before reversing direction, so velocity is 0 there. Next, the acceleration plot has a phase difference of pi or 180 degrees compared to the displacement. Alright, this means acceleration is always in the opposite direction to the displacement. So when the mass is at its maximum position, acceleration is maximum negative, pulling it back toward the center. This is a key feature of SHM. The restoring force and the thus acceleration always points back and toward the equilibrium position. Example 13.5. A body oscillates with SHM according to the equation x is equal to 5 cos 2 pi t plus pi by 4. At t equal to 1.5 second, calculate the A displacement, B speed, and C acceleration of the body. Alright, so using this equation we have to find out the three things. Let's see the solution. So first let's identify what's given. The displacement equation is x is equal to 5 cos 2 pi t plus pi by 4. Here x is the position of the body at time t measured in meters. This equation tells us how the position changes over time as the body oscillates. Time t equal to 1.5 second. Comparing this equation with standard equation of SHM, x of t is equal to a cos omega t plus phi. In this form, a is the amplitude, omega is the angular frequency, and phi is the phase constant. Amplitude a equal to 5 meter, angular frequency omega is equal to 2 pi radian per second. Phase constant phi equal to pi by 4. This value shifts the entire motion along the time axis, meaning the oscillation does not start exactly at the maximum displacement. The phase affects the starting position of the motion. Time period t equal to 2 pi divided by omega, or here omega is 2 pi, so t equal to 1 second. This means the body completes one full oscillation every second. So let's start with part A, finding the displacement at t equal to 1.5 seconds. So we will substitute t equal to 1.5 into our displacement equation. The displacement tells us how far and in which direction the body is from its mean position at a specific time. So x of 1.5 is equal to 5 cos 2 pi into 1.5 plus pi by 4. Alright. Now uh, x of 1.5 is equal to 5 cos 2 pi into 1.5 plus pi by 4. So x of 1.5 is equal to 5 cos 3 pi plus pi by 4. So it will be x of 1.5 is equal to minus 5 cos pi by 4. As we know, cos 3 pi plus theta is equal to minus cos theta. So it will be x of 1.5 is equal to minus 5 into 0.707. So solving this, you will be get x of 1.5 is equal to minus 3.535 meter. This is the displacement of the body at t equal to 1.5 seconds. Negative sign which tells us the direction of displacement relative to the equilibrium position. Alright. So hence the displacement of the particle at t equal to 1.5 second is minus 3.535 meter. Alright. Now uh, now let's focus on part B of the question, which asks us to find the speed of the body at t equal to 1.5 second. Speed in SHM is the rate at which the displacement changes with time. So using equation 13.9, we have v of t is equal to minus omega a sine omega t plus phi. So v of 1.5 is equal to minus 2 pi into 5 sine 2 pi into 1.5 plus pi by 4. So v of 1.5 is equal to minus 10 pi sine 3 pi plus pi by 4. So v of 1.5 is equal to 10 pi sine pi by 4. Sine 3 pi plus theta is equal to minus sine theta. Now v of 1.5 is equal to 10 pi into sine pi by 4. So v of 1.5 is approximately 10 pi into 0.707. So solving this, you will be get 22.2 meter per second. Hence the speed of the particle at t equal to 1.5 second is equal to 22.2 meter per second. Now see, we need to find the acceleration of the particle at t equal to 1.5 second. So from equation 13.11 we have uh, equation 13.1, this one, a of t is equal to minus omega square x of t. So putting the value of time t equal to 1.5 second, angular frequency omega equal to 2 pi radian per second, and displacement x of 1.5 is equal to minus 3.535 meter. So it will be x of a of 1.5 is equal to minus 2 pi whole square into minus 3.535. Solving this, you will be get minus 4 pi square into minus 3.535. So it will be a of 1.5 is equal to 4 pi square into 3.535. Alright. So we have a of 1.5 is equal to 4 pi square into 3.535. So a of 1.5 is equal to 140 meter per second square. Hence the acceleration of the particle at time t equal to 1.5 second is 140 meter per second square. Alright. 13.6 force law for simple harmonic motion. Now we are starting our discussion on the force involved in simple harmonic motion, or SHM. This is a type of periodic motion where the restoring force is always directed towards the mean position, and its magnitude is proportional to the displacement from that position. Let's see how Newton's law helps us understand the force in SHM. So first let's recall Newton's second law of motion. It tells us that the force acting on a particle is equal to its mass times its acceleration. So here the basic equation from Newton's second law, f of t is equal to m into a of t. This means that at any time t, the force F acting on the particle is equal to its mass m multiplied its acceleration at t. Alright. Using equation 13.11, we have a of t is equal to minus omega square x of t. So substitute this expression for acceleration into our force equation. This means we are replacing a of t with minus omega squared times x of t. This step is crucial because it links the force directly to this displacement, showing the unique nature of SHM. So f of t is equal to minus omega square x of t. So f of t is equal to minus k into x of t. So we know k is equal to m into omega square. So omega equal to under root k by m. So consider equation 13.13. This implies that like acceleration, force is always directed towards the mean position. Hence this force equation 13.13 is also called the restoring force in SHM. Alright. Now from equation 13.13 we have F is equal to minus kx. This fourth law is known as Hooke's law, named after Robert Hooke. So this law tells us that the force is directly proportional to x, the displacement. That means if you double the displacement, the force doubles too, but always in opposite direction. A particle that moves under this kind of force is called a linear harmonic oscillator. The word linear comes from the fact that the force depends on x, not on higher powers like x squared or x cubed. Harmonic means the motion repeats in a regular pattern like a sine wave. What happens if the force law gets more complicated? So if the force includes extra terms like x squared or x cubed, then it's no longer just proportional to x. For example, F is equal to minus kx. When the force law includes these additional terms, the oscillator is called a non-linear oscillator. Non-linear means the restoring force does not increase in a simple direct way with displacement. Examples of linear and non-linear oscillators. First, linear oscillators. A classical example is a mass attached to an ideal spring. If you stretch or compress the spring a little, it follows Hooke's law perfectly. Another example is a simple pendulum, but only for small angles. When the swing is gentle, the restoring force is nearly proportional to the displacement. For the simple pendulum, the linear approximation only works for small angles, usually less than about 10 degrees. At these small angles, the motion is regular and predictable, just like the mass on a spring. This is why we use these systems to study basic oscillatory motion. Second is non-linear oscillators, large amplitude pendulum. If you swing a pendulum at large angles, the restoring force no longer follows a simple linear rule. The motion becomes more complicated and the period changes the amplitude. Real springs also become non-linear if you stretch them too far. The force does not increase smoothly with displacement anymore. So real springs under large deformation. Example 13.6. Two identical springs of spring constant K are attached to a block of mass m and two fixed supports as shown in figure 13.14, so that when the mass is displaced from its equilibrium position, the either side it executes a simple harmonic motion. Find the periods of oscillation. So here you have to find out the periods of oscillation. Let's see the solution. To start, let's link about what it means for the block to perform simple harmonic motion or SHM. For SHM, uh, the force acting on mass must be directly proportional to how far it is displaced from its equilibrium position. So we need to show that the force acting on the mass is proportional to the displacement. In other words, if we move the block a little, the force pulling it back should increase in direct proportional to how far we have moved it. This is similar to how a stretched or compressed spring behaves according to Hooke's law, F equal to minus kx. The second requirement is that the force must always act towards the mean or equilibrium position. This means that no matter how which side we move the block to, the spring will always try to pull it back to the center. This restoring force is what causes the oscillatory motion. Suppose we move a mass a small distance x. Alright. Suppose we move the mass small distance x to the right from its equilibrium position. Both springs will either stretch or compress, and we need to analyze the forces they exert on the uh, exert on the block. So the direction and magnitude of these forces will determine if the motion is truly simple harmonic. Now, uh, when displaced by a distance x to the right, left spring gets elongated by length x. This means both springs are either stretched or compressed by the same distance, but in opposite ways. Both springs contribute to the total force acting on the block. So, focusing on the right spring, when the block moves right, this spring is compressed by x. So, the both springs are either stretched or compressed by the same amount, but in opposite directions. The force from a spring is given by F is equal to K into elongation or compression. Here K is the spring force measured in newtons per meter. Alright, and X is the distance the spring is stretched or compressed, measured in meters. The bigger the value of K, the stiffer the spring, and the greater the force for the same displacement. If the elongation is X, then F spring is equal to Kx. Now, let's analyze forces acting on the mass. When the block is displaced, both springs exert forces to restore it to equilibrium. Forces are vector quantities, so direction matters. Force from left spring F1 is equal to minus kx and pulling toward equilibrium, that is leftwards. Force from right spring F2 is equal to minus kx pushing toward equilibrium, that is leftwards. So net force F1 plus F2 is equal to minus 2x. Alright. Now F is equal to 1 F1 plus F2. So hence the force acting on the mass is proportional to the displacement and it is directed towards the mean position. Therefore, the motion executed by the mass in is simple harmonic. Alright, since F is equal to minus 2 kx, this force follows Hooke's law with effective spring constant K effective is equal to 2k. Time period of SHM is given by the relation T equal to 2 pi under root my K effective. Putting the value of K effective, time period of this SHM will be T equal to 2 pi under root m divided by 2k. Alright. Now we will summarize today's lecture in some brief points. Velocity in SHM is the projection of the uniform circular motion velocity on the diameter of the circle. Speed in circular motion V is equal to omega A, where omega is the angular velocity and A is the amplitude. Instantaneous velocity in SHM, v of t is equal to minus omega a sine omega t plus phi. Instantaneous acceleration in SHM, a of t is equal to minus omega square x of t. Acceleration always points towards the mean position. So force also F is equal to ma. Displacement, velocity and acceleration are all sinusoidal functions of time but differ in phase. Phase difference between velocity and displacement is pi by 2. Phase difference between acceleration and displacement is pi. Thank you for your attention. I hope this lesson was helpful.